thought this would be a good chance to give an overall review of the entire class, right? So we began with a battery-powered vehicle lab, and we built a model representing constant velocity motion. Okay? So with constant velocity motion, we found that our position time graph was linear with a slope, and our velocity time graph was a horizontal line. We also found that our equation, our mathematical model for constant velocity motion, which is the equation of this line, is position equals average velocity times time plus our initial position. And if we subtracted our initial position from both sides of this equation, oops, I want final position minus initial position, which is going to be my displacement, and that's going to be equal to average velocity times time. So displacement is average velocity times time. And as you later discovered, the area of our velocity graph is going to be average velocity times time. So there's definitely a connection between these two graphs, which makes sense. After all, they're modeling the same exact motion. So really we have one model here representing constant velocity motion. Okay? Now things get more complicated because our overall objective now is to model a more sophisticated motion. We tried to model a speeding up motion, and on our position time graph, we got this beautiful curve. And on our velocity time graph, now, as you can see, we're getting this beautiful straight line. Okay? And let me go ahead and go through how you did that with Logger Pro. So we're really investigating two relationships. The relationship between position and time, and we're also representing a relationship between instantaneous velocity. That's instantaneous velocity. That's velocity at a moment in time. Instantaneous velocity and time. So there's two separate purposes to this investigation, two separate investigations, if you will. So original data looked like this, and we have this beautiful curve. I can auto-scale my graph to make it look a little better. Okay? And then I can add some pages. Page, add page, copy current page, hit OK. Page, add page, copy current page, say OK. Page, add page, copy current page, and say OK. All right? So I'll go back to our original data, page 1. You'll notice the slope is gradually getting steeper. What does this mean, right? As this tangent line gets steeper, this little tangent line here, this black line you see, gets steeper to represent our increasing velocity. As our slope gets steeper, you notice down here, at 0.7 seconds, our slope of this tangent line, this line tangent to this beautiful curve you see, the tangent line slope is 3.8 centimeters per second, meaning at 0.7 seconds, at this moment in time here, our velocity, our instantaneous velocity, is about 4 centimeters per second. Later on, we have a velocity of about 17 centimeters per second at 1.7 seconds. And then gradually, the slope gets steeper. Now the slope is 30 centimeters per second at 2.8 seconds. And the slope gets even steeper later, 36.5 centimeters per second at 3.6 seconds. This represents the speeding up of the object as time goes on. So the steepness of the slope, just like before, just like the last unit, the steepness of the slope on a position time graph in physics is still going to tell us our velocity. The only difference is now we have to take the slope of a tangent line since we can't take the slope of a curve. All right? The only way to take the slope at a moment in time on a curve is to draw a tangent line, okay? So now, after that, you made an equation for this beautiful curve. You went analyze, model, and it wasn't proportional, it wasn't linear, it was a quadratic equation. And if I change these two terms here to 0, okay, so I take my b term and I turn that to 0, and I turn my a term into 0, what you'll see, sorry, not my a term, I'm going to turn my b and my c term to 0. There we go. Turn this one to 0 as well. Just to keep things simple. Now, since my b term is 0, b times t is 0. Since my c term is 0, that term disappears. And I just have position equals at squared. So let's see if that's close. And what you'll find is right about there. Let's see. Okay, right about there, maybe a little less. It looks like I have a pretty good fit of my data. Maybe I want to play with these numbers a little bit so that it fits a little better. Let's see, I'll just keep playing a little. Maybe I can make this a positive number. It'll fit a little better. Maybe I make this a negative number. My b and c terms look like they're very close to 0. And my a term looks like it's about 5. So I'm just going to come up with the best fit I can do. I'm just going to visually inspect this position time graph and fit the curve to my data. And then I'm going to click on Create Calculated Column. Okay? What this will do is Logger Pro is going to take this equation. It's going to plug in these values of a, b, and c into that equation. Plug these values into time. And it's going to calculate this beautiful black curve you see there. Okay? So I'm going to delete this ink so you can actually watch it do this. Let's see if I can delete this part too. Okay? Oh, I need to delete this part. There we go. So I hit OK, and you'll notice we have this beautiful column here that was just created that basically tells us, let me move this over so you can actually see it. This is a best fit curve of our data. So if I double click here, it'll take me to a new window, and I can type in best fit curve. Okay? And then this is a best fit curve representing position. So I need to write position. So I've taught Logger Pro now how to make a best fit curve of my data. So I'll write X for best fit curve, because it's still fundamentally representing position, okay? And the units are centimeters still for position. And you can see in this window here, that's the equation that Logger Pro is using to calculate its best fit curve, okay? So I'll hit done, and now I have a labeled column, and I have a close approximation of my data. It's not going to be perfect, but it's quite reasonable. It's definitely a good model for the motion of our object, okay? And the next thing I had you do, next thing I wanted you to do, is to go back and address this second purpose, which is how is velocity, instantaneous velocity, changing for each moment in time? Not how is position changing. We have an answer for that. We have an equation for that. But how is instantaneous velocity related to time? Okay? And in order to do that, there's a nice way where Logger Pro can actually find the slope of the tangent line for all of our data. Let me show you how to do that. Okay? First, I'm going to make my data table bigger so you can actually watch Logger Pro do its thing. All right? I'm going to make a new calculated column right there, new calculated column. I'm going to call this column instantaneous velocity, okay? That's instantaneous velocity. This is the velocity at a moment in time, okay? And I'll just call it V with an INST at the end, okay? The units I'll give it are centimeters divided by seconds. Those are the units for velocity. And now here's the cool part. We're going to just tell Log4Pro how to calculate it. Now, Log4Pro has a lot of functions in it. It has a ton of them. This is a calculus function. And calculus is actually built on this idea of derivatives. This is what you learn in the first half of calculus. You learn how to find the slopes of tangent lines. Now for us in physics, the slope of a line tangent to a position time curve is our instantaneous velocity. So in other words, the derivative of, let's see, position. Oh wait, I don't want position. That would be a mistake. I don't want the derivative of my data, because that's going to be a little bit sloppy. See, if I take the tangent lines of data, it's going to look like this. It's going to take the slope from those two, from those two, from those two, from those two. It'll work, but it just won't be as beautiful as if I take my best fit curve and take the tangent lines from that. It's going to be a lot more beautiful. The data is just going to come out a lot cleaner, a lot nicer. It's not real data anymore. It's actually based on a best fit curve of our data. So it is a little bit different. So again, I'm going to use a calculus function called derivative. I'm going to go variables, and I'm going to use my best fit curve. So best fit curve is what I'm going to use. And then I'm going to use time on the horizontal axis. So what this means is, hey, Log4Pro, please take the slope of all my tangent lines that are tangent to my best fit curve on my best fit curve position time graph. Okay? So I'll hit done. And I also named that column velocity. So now I'm ready to go. And again, if I go to best fit curve position, this is my beautiful best fit curve. And Log4Pro has taken the slope of this best fit curve at all the points using the tangent line technique. So it's drawn all these tangent lines and found the slope of those tangent lines. And that's how we got a column called instantaneous velocity. And you can see how beautiful it is. It just comes out perfect. And this is just asking for a best fit line. And we're going to want to make an equation for this best fit line. Okay? So your equation is going to be V instantaneous for instantaneous velocity equals, it looks like 9.9, so why don't I just call it 10 centimeters per second divided by seconds, okay? So you definitely want to try to figure out what this means. That's pretty cool. And then times time. And then it looks like 0.1, so I'm going to say plus 0.1 centimeters per 1 second, okay? And if you look at these units here, it should be a clue that that's a velocity. Now, if I plug in 0 seconds for time, this entire term here, because time is 0, this entire term would disappear, right? And so I would end up with a velocity equals this. So basically, this is my velocity when? You should see that this is our velocity at 0 seconds, okay? That's kind of cool. And then if I go back over here, let me fix this again, okay? This said 10 centimeters per second divided by 1 second times time. So fundamentally, this is telling me that every second my velocity must be changing by a certain amount. And here in this case, it looks like 10 centimeters per second. So every second velocity of the object is changing by 10 centimeters per second. That's pretty cool. We can write this as a general equation now, where V, instantaneous.